All right, it's the home stretch, the last assessment of the semester of 2021 this year. So that's pretty wild stuff. We're going to solve logarithms, and you are allowed to use a calculator because we're going to do some messy ones. So let's go through a couple of types of problems you're going to see. If you can do this, you can do the test. First one, you have a log that is already isolated. So I will now rewrite it as an exponent. 2 to the fourth equals 1 minus x. 2 to the fourth, 2, 4, 8, 16. 16 equals 1 minus x. So 15 equals negative x. That means x equals negative 15. So the first thing you're doing is taking the log and then writing it as an exponent. Now for the next one, I'm going to undo the exponent. Another way of thinking about that is rewriting it as a logarithm. But I think most of the time, we're going to think about it like this. Take the base 5 log of both sides. The base 5 log of 26. When you do that on the left side, the base 5 log and the base 5 exponent cancel out. Or the base 5 base, I guess. Base 5 of the exponent gives you this. And then that's the base 5 log of 26. So you need to be careful. To solve x, the first thing you're going to do is subtract 5, and this becomes a little bit of calculator work. So you got to kind of follow along here. I'm going to do the log base 5 of 26. Now it's a two-step equation. I don't need that. This guy, the first thing I would do is subtract 5 minus 5 because I have this plus 5, and then I will divide by negative 3. Divided by negative 3, and that is 0.9919. So x equals 0.9919. These are good problems to check, so let me show you how to check it. Store it as a variable. I always pick a. 5 to the power of 5 minus 3a. Hopefully I get 26. Good, I know I did it right, so 0.9919. If it's a base e logarithm, that's what natural log is. I'll write this as e to the 14th equals 2x minus 3. E to the 14th is some horrible decimal, so I'll use a calculator now to say e to the 14th. And I'm going to solve this, I'm going to have to add 3, and then I will divide by 2, and I will get x equals, holy cow, hold on a minute. I think I typed something wrong. E to the 14th, no, that's it. It's just humongous. 601,303. Okay, 601,303.6421. 601,303.6421. So big number. Okay. Let's try another one. So this guy has two logarithms. So the first thing we need to do is condense them. And remember, addition condenses into multiplication. So I have this equals the log of 12. Now, notice we're taking the base 10 log, the common log of both sides. So what I'm going to do is say, well, look, these arguments have to be equal. X squared plus x has to equal 12 for this to be true. And then you can subtract 12 on both sides and factor. So what multiplies to negative 12 and adds to positive 1? X plus 4, x minus 3, which means x could be negative 4 or x could be 3. Or could it? So we have to be careful. The domain of logarithms is restricted. You can't take the log of a negative number. So if you try and plug that in right there, it can't be negative 4. Can it be 3? Log of 3 is fine. Log of 3 plus 1, yeah, that's fine. So it can be 3, but negative 4 is an extraneous solution. What else you got? All right, so now we have an exponential. The first thing I would do is multiply both sides by the denominator. So 3 times e to the 2x plus 1. I'm going to go ahead and divide by 3. So if I divide both sides by 3, now I have 3 equals e to the 2x plus 1. Subtract 1, 2 equals e to the 2x. And now I got to go to calculator mode. So the first thing I would do is take the natural log of both sides. That'll get rid of the base e, and then I'll have to divide by 2. I get 0.346, we'll say 3.3466. X equals 0.3466. Okay. What about here? Divide by 3 on both sides. The base x log of 9 is 2. X squared is 9. When you rewrite it as an exponent, x equals 3. X can't be negative 3 because the base can't be negative for a logarithm. Rewrite as an exponent. It's a single log. 8 to the 1/3 equals x over 5. Remember, that's cube root. Cube root of 8 is 2. Multiply both sides by 5. X equals 10. This is about as bad as they get. So when you do these, I've gone both ways. I think the better way to do it is to pick the ugly base. If you have an exponent that's messy, that's the base I'm going to try. So I'm going to do the base 3 log of both sides. They have different bases, so this is all you can do. Base 3 log of 3 to the x minus 2. Now on the right, you get x minus 2. But on the left, you're going to have to bring the 2x down. So 2x times the base 3 log of 2. So now you got to realize that this is some product. Okay, this is some nasty number, and it's a decimal. So I have 2 times x times the base 3 log of 2. 2 times the base 3 log of 2. It's that many x's on the left side. 1.2619. 1.2619 x's on the left side. I think it helps people see this because now when I subtract 1 x on both sides, I get 0.2619 equals negative 2. So I'm going to subtract 1, and I have 0.2619x equals negative 2. So negative 2 divided by that will give me x by itself. And that's negative 7.6377. X equals negative 7.6377. Those are about as tough as they get. So you probably want to go back and look at some of the problems where there's 2 different bases. So that's just basics, like just straight up solving, no thinking about the problem. Now we'll do some problems where you have to create a model and then solve it. So this one says we had 30 stray cats. That's an initial amount times the growth factor is 15. 100% plus 15% is 115%, which is 1.15 to the t. So the population after t years is 30 times 1.15 to the t. Okay, you want 4 years? Well, I have to get the model right to be able to do that. So 30 times 1.15 to the 4th. So that's about 53 cats. Again, you round up. 53 cats. Any decimal. Population, you always round up. 53 cats. When will it reach 500? 500 equals 30 times 1.15 to the t. So to solve this, get the exponent by itself. 500 divided by 30. 16.6 repeating. Now I'm going to take the base 1.15 log. So I'll use my log base formula. 1.15 of that. And this will tell me 20.13 years. About 20.13 years. T equals 20.13 years. So that would be, where's my, from 1999, so 2019. We'll have gone from 30 cats to 500 cats. Okay. Newton's law of cooling. Okay, so we'll do Newton's law of cooling problem. Remember, the big thing about these is that D sub 0 is the temperature difference. It's not the initial amount. It's not 98.6, and it's not 50. It's 98.6 minus 50. So we're going to say the initial temperature is 50, or the surrounding temperature rather, plus the temperature difference is 48.6, and my constant is 0.1947 to the t. So this is the temperature after t hours. Right there's my model. If the temperature is now 65, okay, 65 equals 50 plus 48.6. I keep forgetting to write the e. E to the negative 0.1947t. Look, the equation has e in it. I keep forgetting to write the e though. So I will now subtract. I'm going to see if I can do this all in the calculator. 65 minus 50. Now I have this by itself. Divide by 48.6. Now you have e to the power of, so undo that using natural log. Now you have the exponent by itself, divide by negative 0.1947, and you get 6.03, so about 6 hours ago, which I feel like that was the answer to the other one I did, about 6 hours ago. The person died about 6 hours ago. So you subtract, you divide, then you undo the base e using the natural log. Last one, what's the initial amount? Remember, this is PE to the RT. This formula look like that. You can just plug in T as 0 as well, but it's 100. There's 100 bacteria at the start. After 6 hours, I'll plug in 6, 100 E to the 0.693 times 6 hours. So there's 6,395, 6395. Remember, round up, 6395 bacteria after 6 hours. And then the last one, when will it reach 15,000? So 15,000 equals 100 e to the 0.693 t. So I divide 15,000 divided by 100. Take the natural log of both sides, and then divide by the decimal, 0.693, and that gets you 7.23. About 7.2 hours. After about 7 hours, we'll have gone from 100 to 15,000 bacteria. So that's a lot. If you can do the study guide, you can do the tests. Let's quiz. It's our last assessment of the semester. Good luck. Hit that like and subscribe, and congratulations on making it to the end of the semester.